invitation. Thank you for having me. This will be a disclaimer. This is probably a pure math talk, but it's been arranged in such a way with the change of schedule that you will see the physics applications in the next two talks. I'm going to build the math background for what we're going to see later on. And here's like a quick overview. I'm going to talk to you about partial flag varieties. I would say maybe my favorite spaces in algebraic geometry. And I will motivate them from physics, so at least you can know why we're going to listen to this math talk. Then I'm going to go through the definition in case there's someone here who hasn't seen them yet. So please bear with me. The ones that are very familiar with the topic, it's just take it as setting up notation. And then I'm going to go talk about the cluster structure, and in particular emphasize what nice consequences it has for a space to have a cluster structure, going through some geometric parts of it, tropical geometry, and combinatorics. And lastly, I'm going to present a result in collaboration with Jianrong Li, where we were able to relate the cluster algebra structure on flag varieties to the cluster algebra structure on Grossmannians. And please feel free to interrupt me at any point during the talk if you have any questions. Okay, so let's start with the physics motivation. We've seen this part already. It popped up in James' talk, among others. So if we are in the situation of scattering of n particles, light-like, and we pass through the momentum twistor parametrization, we end up with n points in CP3, and we assume we have an ordering on that, which corresponds to planarity. So this corresponding configuration space can be parameterized by these 4 minors of a 4 by n matrix, and it is closely related to the Grossmannian 4n. In this talk in particular, I want to generalize this setup a bit, and we've also already seen this generalization in James' talk. So if we now drop the condition of dual conformal symmetry, we can do that by introducing another infinity twistor that is a line spanned by 2 extra points in CP3, and our configuration space will now depend on the endpoints we had before plus the extra line. So if we want to parameterize this space, we can do it in a very simple manner by taking 4 minors, only that now our configurations depend on the line spanned by n plus 1 and n plus 2, and not depend on n plus 1 and n plus 2 separately. So in the parametrization, this is reflected by taking 4 minors whose indices run only between 1 and 2, and minors that contain simultaneously n plus 1 and n plus 2. So this configuration space is called the momentum twistor variety, and its affine cone again is closely related to a partial flag variety, or a decorated version of it is the affine cone of a partial flag variety, and the partial flag variety of interest here is a 2-step flag variety. So we have in Cn 2 vector spaces, v1 sitting inside v2, dimension of v1 is 2, dimension of v2 is 4. And yes, any questions at this point?
So should we think about this brackets, 2 brackets as spinor hasty variables, really?
Yes, you can, but it's not the spinor helicity parametrization. I'm not having the square brackets, right? Just having the two brackets and the 4 brackets from momentum twistors. Okay, great. So that was essentially the physics part of my talk. I'm going to comment more on what we're going next with this.
Sorry, can I ask, maybe this doesn't matter, but should you motto by the torus action?
That's why I have this affine cone thing here. For the momentum twistor variety, you want to motto by the torus action. But I'm using this as a motivation to get to the flag variety where I do have this section.
Maybe this means nothing, but you introduce the infinity twistor using 2 points, n plus n2.
Yes.
But nothing can depend on them individually.
Exactly. Yes. And that's reflected in my parametrization. So in the parametrization, the minors I choose, I have this matrix n 4 times n plus 2, but when I parameterize the momentum twistor variety, there is no minor that will either contain n plus 1 and not n plus 2 or the other way around. So in the end, my parametrization remembers that I only depend on the two appearing together. Exactly, thank you. Okay. So then let's go to partial flag varieties, how they appear in math a bit more generally. And here's the definition. So I had, in this case before, I had two vector spaces in my flag. A flag is a sequence of vector spaces, one contained in another, and two fixed dimensions. And I can generalize that. I can also change my field. This doesn't really matter. But so I can fix a sequence of integers between 1 and n, d1 up to dk, and for every such dimension vector, I require to have a vector space with this dimension in my flag. And okay, if I want to now study partial flag varieties, how can I grab them and handle them? Well, I can remember the Grassmannian, and that every vector space in my flag is a point in a Grassmannian, so I have this very natural embedding of a flag variety into a product of Grassmannians, and then I have access to the Plucker embedding of each Grassmannian, which gives me a Plucker embedding of the partial flag variety into a product of projective spaces. And my notation, this will be the notation for the homogeneous coordinate ring, and I'm going to pick that up later on the slides. So more precisely, what are the coordinates on the projective spaces? Well, they're the Plucker coordinates of the embeddings of the Grassmannians. So how do they evaluate on a point of a flag? A point in the flag variety. So if I fix a flag, I can represent it by a matrix by choosing first the basis of the ambient space and then a basis for my flag that is such that when I run through the basis, the first di vectors always span, the first di vectors span the di vector space in my flag. And I'm going to do that row-wise. So vi is generated by the first di rows of n, right? I get the matrix by just expressing the basis for vi in the canonical basis of my ambient space. And then the Plucker coordinate is a minor on this matrix. It will always be a minor where I choose the first di rows, as those are the rows corresponding to my basis for vi, and then the columns can vary. And here's a small example in case you haven't seen that before. Yes, okay, so these are my conventions. My matrices span row-wise the vector spaces in the flag. Any doubts on this? Okay. Great, so now we can, that's the setup. So now let's see the interesting parts of these spaces. So they have a cluster structure. And what I mean by that is that this homogeneous coordinate ring of the Plucker embedding of the flags varieties is a cluster algebra. And I'm going to define a cluster algebra in like a few slides, but it's a bit of a, there's a few ingredients to the definition. So I first want to tell you what's great about having a cluster structure, and then I'm going to give you the technical details of what it means. So the result I'm citing here is the first paper that showed in the generality I'm having here that this ring is a cluster algebra. That's work by Geisler, Clerc, and Schröer from 2008. But by now we have more general results by Kadem that showed that we can actually generalize this to other simple groups. So the flag variety I showed you is a quotient of the special linear group, SLN. But I can replace this one by any other simply connected semi-simple complex algebraic group, take quotients by parabolic subgroups, and they will also have the property that their coordinate ring is a cluster algebra. And in particular, maybe some of you might be interested in Lagrangian or orthogonal Grassmannians. They also inherit a cluster structure through this more general construction of Kadem. Okay. Good. So then let's have my advertisement slide on cluster structures and why I like them. And I'm going to present this in an example of a very small flag variety. So the flag variety 1, 2, 3, those are flags, two-step flags in C3, complete flags in this case. And I'm going to consider here the affine cone to not worry about taking torus quotients too much. And the cluster structure is also more visible on this level. So this flag variety, if I can consider it, okay, oh actually, yes. Right, so I pass to the affine cone, which now means I don't need to be in a product of two affine spaces anymore. I can just take the product of the affine spaces, and I'm just in one C6 instead of having the product of the affine cones of the two projective spaces. And my flag variety here is given by a single metric of this form. The cluster variety that lives inside of it consists of two algebraic tori. So I have two copies of C star to the 5, and they have coordinates. I think this one does not point, right? Oh, it does point. Okay, here. And these are my coordinates. So the PIs are Plücke coordinates, and I have a collection of 5 corresponding to each of these algebraic tori. And then the cluster variety is the union of these two tori glued along the birational map, where I have this transition function. So my map is pretty simple. 4 of the entries of my coordinates don't change, and just one entry has this kind of Laurent binomial transformation. And if we look at this map, there's a few observations we can make that also hold more generally. And that is that all the expressions in local coordinates appearing are Laurent polynomials without any minus signs. So in particular, this cluster variety is not only well defined over the complex numbers, but I can also pass to semi-fields such as the real positive numbers or even tropical real numbers. In particular, every cluster variety or every variety with a cluster structure has a positive parametrization arising from the algebra structure, and it comes endowed naturally with a positive part. The theory of cluster variety goes even a bit further, and we also have a theory of divisors and how to extend the volume form we have on each torus to the cluster variety and to the compactification of it. So the torus has the canonical volume form, just 1 over the product of all the variables. And it patches through the gluing map and also defines a volume form on the whole cluster variety. And now the flag variety here. So in the cluster variety, none of my coordinates can vanish, right? Because I just have 2 copies of C star. But on the flag variety, I know that some Plücke coordinates might vanish in certain points. So the flag variety is actually the cluster variety together with the divisor that has 4 components, which is exactly the vanishing of these 4 Plücke coordinates. And the theory of cluster algebra, so cluster varieties, tells me that with this particular choice of prime non-crossing divisor, or like every component is like non-crossing boundary divisor, the volume form I have extends, and it has a unique simple pole on every component of the divisor. So in particular, this is the definition of a log-Calabi-Yau pair. Okay. That's it on cluster varieties. Are there any questions? Okay, so then let me move on to one nice implication of this observation that we made here, that a cluster structure gives us a positive parametrization. So in particular, we can tropicalize a cluster variety by taking the tropicalization of a torus, which is just the real vector space of the corresponding dimension, and tropicalizing this transition function that would just mean replacing the pluses by taking the maximum and the multiplications by taking the sum. And if we do that, that's readable, yes. So we get a fan in a real vector space. So in this case, I changed my example. From the cluster algebra point of view, this is the same example, but I took this from another slide where I was talking about Grassmannians. So the Grassmannian, like my example before, is just a quadric in a C6, or it's affine cone, and it has these two torus patches coming from the cluster structure. So if I now decide to work over the tropical real numbers instead of the complex numbers, what I obtain from these two torus patches is a fan that lives in R to the 5. And the way I get it is exactly by taking this transition function I had on the slide before and considering where are its domains of linearity after tropicalizing it. So my function had a maximum coming from this plus. It has just two terms that I'm taking the maximum over, so I only have two cones that would correspond to where in my space the first term wins the race of being the maximum and when the second one wins the race of being the maximum. So in this small example, this amounts to these two cones in R to the 5. I don't know if it's very readable. But so this is the relation defining. This is also the relation we can read the gluing map from by taking one of the terms P13 or P24 to the other side. And then here I can see, okay, so when U12 plus U34 is greater than the other term, tropicalized, that is one domain of linearity of my map. And if the greater equal sign flips, that's the other domain of linearity. So I get this fan naturally associated with my cluster variety. And this fan, more generally, is known as the G-vector fan. This is just maybe a non-standard way of computing it. And the embedding that I have from the Grassmannian into the projective space, its Pulcher embedding, or here the version of the affine cone, also gives me a tropicalization by just tropicalizing the ideal that defines my variety. So in this case, the tropicalization lands inside a vector space of dimension 6, one dimension higher, because we're taking all the coordinates into account. And in that vector space, in this case, I have 3 maxima cones in the tropicalization. And if I now take the map that is embedding one of these cluster charts into the Grassmannian, that's also tropicalizing the transition function we had on the other slide. This also gives me a map between these two tropical spaces. So on the one side here, I have the fan living in R5, and on the other side, I have the tropicalization of the ideal living in R6. And this is the transition, or this is the embedding, the tropicalization of the embedding. And the observation in this small example is that the 2 cones I have on the left-hand side map to 2 out of the 3 cones I have on the right-hand side. And the 2 cones they map to actually correspond to the positive part of the tropicalization of this ideal. And this result holds more generally. I've stated it here for the case when my atlas of cluster charts is finite. And in that case, it generalizes on the nose. So whenever I have a finite type cluster algebra and I run this construction of tropicalizing each chart and checking what are my domains of linearity, the fan I obtain is isomorphic to the positive part of the tropicalization I have on the right-hand side. So this is a map of fans. Yes, and there's approximations of this if I have an infinite atlas, where I can always cover finite parts of the tropicalization. Have any questions?
So maybe it's related to your last comment. So if the space is big, the thing on the right-hand side is always finite, right?
Yes.
But the G-vector fan will not be.
No.
So the image must be bigger than the thing that you get on the right.
Right. Yes. So, if I want to have like this nice matching of fans, so the nice observation here is that the cones really match, right? One cone here goes to a cone here, and cones on the left are always simplicial, so I know I would hit simplicial cones on the right. So what I would do to generalize this result is work with my embedding here, manipulate it in such a way that it is compatible with a finite choice of seeds that I would have on the left-hand side. So I can always choose this embedding so that a finite collection of seeds here or a finite collection of cones in my GFAT maps to a finite collection of cones in the tropicalization. And I would have this identification there. But yeah, you're absolutely right. As the left-hand side would have an infinite fan, we will not have the isomorphism of the fan structures in.
What is FG trop?
Oh, it's what I described. It's called the Fock-Onstrop tropicalization.
Okay.
So this whole theory of cluster varieties, and it's essentially a scheme-theoretic approach to cluster varieties where you change your base field to be a tropical field.
Nice.
Okay, great. So this was the part on the geometry. Then let me move on to a more combinatorial way, or like first give you a review of what cluster algebras are. So in case you were lost for the last 2 slides, you can come back if you want to know what cluster algebras are. Just 2 slides and then go back to your exercises. So cluster algebras are commutative algebras, and they come equipped with a special set of generators called cluster variables, and these cluster variables are grouped in clusters. Clusters are maximal algebraically independent subsets in my algebra. And also I have special automorphisms on the cluster algebra called mutations that take clusters to clusters. And the whole data of all of this is usually encoded combinatorially in a directed graph, which in algebra we call them quivers. Just to make sure we're associating algebraic data to these objects. So the smallest non-trivial quiver I can imagine is one with 2 vertices and 1 directed arrow from 1 to 2 in my example. So I can take this combinatorial object to generate a cluster algebra. So the first thing I do is associate a cluster variable to every point in my quiver, to every vertex in my quiver. And then I need to tell you what the mutation rule is so that you can generate new clusters from the one I've given to you. In this case, the mutation rule is this simple rule. So my clusters all have 2 elements, xi plus 1, and this is the mutation rule. So if I want to generate the new element xi plus 1 from xi and xi minus 1, I just use this little mutation. So if I run through this construction and just generate all the xi's that I get from this formula, in this example, you will observe periodicity after 5 steps of mutation, where the variables start to repeat. And once I'm at this point, I can generate the cluster algebra as a subalgebra in this ring of rational functions generated by my first cluster. And it's generated by all the cluster variables that I found along the way of my mutation. And this definition generalizes. If I don't have periodicity in my system, I would just have to go on and collect all the infinitely many cluster variables to generate my cluster algebra. So this mutation rule, which I just gave you here directly for the small example, is also encoded by the quiver. And this is how the construction goes. So if I have in my quiver, I have certain vertices that I deem mutable, and those are the ones where I can perform this mutation in order to generate a new variable associated to exactly that vertex. And locally in the quiver, I will only focus on my vertex that I've chosen for mutation k and arrows that relate to this vertex. So if I see a configuration like this around a mutable vertex k with a arrows from I to k and j arrows from k to j, b arrows from k to j, and maybe some number of arrows between I and j. I just put an arrow with both directions here to notate that c would be a positive number if the arrow goes from I to j, and negative if it goes from j to I. So then mutation at this vertex k would change the configuration like this. I change the direction of all the arrows from I to k and the ones from k to j, and I adapt the number of arrows I have between I and j with this formula. Okay? So as c could be negative, this could also cancel all the arrows that I had between I and j. And then I also operate on the set of cluster variables, and this is the formula how I replace one cluster variable by the new one for the next seed. Okay? And a seed is a pair, quiver, and tuple of cluster variables. Okay. Any questions on this? I'm also happy to explain again. If anyone hasn't seen cluster algebras and wants to know more, I'm happy to talk about that. Okay, so then let's get back to the partial flag variety and how to get its cluster structure. And here's the construction. So in order to give you a cluster structure, I need to give you a quiver, and I need to give you a set of cluster variables. The quiver, I will get it from drawing a wiring diagram, like a graphical representation of a certain permutation. And for my flag variety with dimensions d1 to dk in n, this is the permutation I choose. And then once I've drawn this permutation, I can associate the quiver by taking essentially the dual graph, and I will go through that construction a bit. And then I can construct a cluster in terms of Pluko coordinates, which I can also, or first in terms of minors, which I can read off the wiring diagram. And so I commented before that these cluster algebras can be infinite, and here's a list of examples where they're not for partial flag varieties. So we have, in the case of Grassmannian, we have some examples of finite atlases or finite number of seeds, and we also have some examples in flag varieties that are no longer Grassmannians. Okay, so then let me tell you about the construction. Any questions?
The classification of finite mutation type. There's also this kind of intermediate step. Right?
Yes. So there is. I think there's a classification of which quivers have finite mutation type, but I don't know in terms of flag varieties which of those are like realized as flag varieties. Okay. So then, here's an example. How readable? Yeah. Oh, it's very readable. It's actually more readable for you than it is for me. So, so what I've drawn here is in green. Okay, so the colors maybe not. So these are like kind of teal green colors, the ones that are not arrows. That is drawing out the permutation. So the permutation that I fixed sends 1 to 6, 2 to 7. 3 goes to 3, 4 to 4, 5 to 5, 6 to 1, and 7 to 2. That's the permutation for this flag variety, which is 2, 5, and 7. And I draw out a wiring diagram for it, and then I associate these index sets to the faces that are either bound or unbound to the left in my diagram. And the index sets I associate are all the indices of lines that pass northeast of the face. So for example, this 5 up here is 5 because the only line to its northeast is the line labeled 5. And the labeling of the lines, I read it off from the bottom of my diagram. Oops. Okay, so that gives me certain index sets, and I will tell you how the index sets help me to associate cluster variables. And the quiver is also obtained from this diagram. I have three generic types of arrows and then 2 special arrows. So first of all, I always have arrows passing through these line segments that are parallel, that are horizontal or that are vertical. So they go down or right. And then I have these diagonal arrows passing through crossings of 2 lines. And there's 2 vertices that don't really fit into this diagram, at least they don't correspond to faces. And they will always correspond to the dimension vectors in my sequence. So I have 1 extra vertex for every dimension vector in my sequence. And yeah, there's a rule of how to connect those arrows as well, but I would like to skip it here. So once I have the quiver obtained from the diagram, I only need to tell you what are the cluster variables I associate with the vertices, and then you're free to start playing with the cluster algebra and generate all its other cluster variables. Any questions on the picture? Good. So then here's how to get the cluster variables. So the index sets that I've read off my diagram, I use them as row index sets of minors, and the column index sets on the minors will always be the right bound columns in my matrix. So these minors actually are not minors that live in the homogeneous coordinate ring of the flag variety, but rather on an affine variety that embeds into the flag variety. And this affine variety is the unipotent radical of the parabolic subgroup defining my flag variety. I've avoided talking too much about this, how to present flag varieties as quotients, but I wanted to include this example to at least give you an idea. So the flag varieties I'm talking about, they're quotients of SLN, and they're quotients of SLN by certain parabolic subgroups, which for me will always have this form. They're matrix subgroups with containing all the lower diagonal and some entries above the diagonal. And then from this parabolic subgroup, I can pass through to a unipotent subgroup that looks a bit like its opposite. So whoever had zeros in the parabolic subgroups, I will be free to choose entries in the unipotent subgroup. And the unipotent subgroup has ones along the diagonal. And the minors that I read of my diagram are minors on these types of matrices. And there's an embedding of matrices of this form into the flag variety by exactly taking rows as generators for my vector spaces. And having this embedding of the affine variety into the flag variety, I have a map, a projection in the other direction between the homogeneous coordinate rings, and I will use that map to lift the minors to actually be elements in the cluster algebra. And this is now in the paper of guys like Jack and Schroer that tell us there's a unique lifting of all the minors that I can read off my diagram. And here's an example for how that looks. So for example, in my diagram, I had the index 4 appearing in some region. So that means this corresponds to the minor 4, 6 on the unipotent radical, which is the same as taking the minor 1, 2, 3, 4, 1, 3, 6, 7. This is like, you can compute that with Laplace or just sit down and compute it directly. And this one has the shape of a Plücke coordinate, right? Remember, my Plücke coordinates always had row indices that are intervals starting at 1 and column indices that change. So making this change, I now have a minor that looks like a Plücke coordinate, and it lifts to be this Plücke coordinate.
Sorry, what are the D's and N in this example?
The what?
What are the D's and N in this example?
So we're in the case 2, 4. No, so this is 2, 4, 6. Yeah, 2, 4, and 6.
Ah.
Down here, yes, I swapped. Up here I have the example 2, 4, 5. Now I'm doing 2, 4, 6.
So how can you have like a 7?
Oh yeah. Oh, that's a good point. No, that's a typo. Yeah, there should not be a 7.
Okay.
Yes, definitely a 7. I think I changed the example. I first did 2, 4, 7. I thought it was too big, and then I downgraded it to 2, 4, 6.
Okay.
Yes.
So the second set of indices should be 1, 2, 3, 6 here?
Yeah, this should be 1, 2, 3, 6. Yeah.
Okay, there were some omegas on the previous slide, and will you tell us how the omegas?
Oh, the omegas. Oh yeah, so the omegas, in terms of Plücke coordinates, they're correspond to intervals 1 to the I. Yeah, exactly. Yes, thank you. Okay. Great. So one interesting observation we can make in this example already is that minors not necessarily are after lifting equal to Plückers, but they might be quadrics in Plückers. And this is one of such examples. When we lift this minor 4, 5, 4, 6, 5, 6, we get a degree 2 expression in Plücke coordinates. Okay, so great. I need one more ingredient before I can state my result, and I'm aiming here to relate now two cluster structures, the one on the partial flag variety with the one on Grossmannians. And there's like within cluster algebras, I think it was a discussion for a while what should be like the right notion of having a subcluster algebra with what kind of compatibility of the cluster structures, which if I just take any subalgebra is definitely not given. So here's a definition by Lauren together with Sergey and the book they're writing that was started with Andrei, I guess, Zelevinsky. So if I have a quiver that determines some cluster algebra, and I split the index sets, I partition the vertex sets into two components, and in such a way that there's no mutable vertex in one component connected to any vertex in the other component, then I can do this procedure of restricting the seed by just deleting all the vertices in the index set J. And what I get is called a restricted seed, and if I take this restricted seed to generate a cluster algebra, I will have compatibility, like the mutations kind of run parallel, wherever I can mutate in the restricted seed, I can also mutate in the other seed, so I get what is called the cluster subpattern and the cluster subalgebra. And this is exactly what we observed between cluster algebras for partial flag varieties and Grassmannians. Is there any question on the notion of subpatterning?
So for example, like in A2, I mean, can I find some pattern there?
So in A2, like you just split your vertex set in two, if it should be non-trivial, yeah. Get rid of one vertex and you have...
So what will I see? What is the subalgebra in that case?
It would be an A1 cluster algebra where you just have the two cluster variables. Yeah.
Maybe it's good to mention that sometimes it's helpful to, you can also have this flexibility of freezing some
Yes.
along the way if you can't find it.
Right, yeah, that's a very good point. I will need that. I will totally need that. Exactly, yeah. So the operations I can do on the vertices before splitting is freezing them, meaning like not allowing any mutation anymore there, which helps me to fulfill this first condition of not having arrows between mutable vertices in I and vertices in J.
Sorry, what does arrows between mean in terms of the direction?
Just in any direction. So just like I consider the vertex set of the quiver, I partition it, and I don't want any arrows between the mutable vertices in one part of the partition and any arrow on the other.
But can you have arrows going like the other way?
No, neither way. I'm not specifying the direction of the arrows. Just
Okay.
no arrows.
So, sorry, for A2, I mean,
Yes.
don't you have an arrow? Sorry,
Yeah, oh, yeah,
what was the
yeah.
A2 example?
Yes.
Second set is empty set in A2.
Empty set.
Yeah.
Or you do what Lauren just mentioned, you freeze one of the vertices. Because here we only have the condition on mutable vertices on one side and any vertex on the other side. So if you freeze the ones in I that have arrows to J, then you satisfy the condition.
Okay, thank you.
So if I take a quiver and then sub-quiver, just let's say connected,
Yeah.
will I get the cluster algebra associated to this sub-quiver when I do that?
Yeah, so what you would have to do is exactly the operation Lauren mentioned, freeze anything that is connected, and then, yeah, you have the subgroup. So I will have an example of this as well. Let me first state the result, and then go like towards the proof, and show you a big example. So if I'm in a partial flag variety with indices d1 up to dk, I will consider a Grassmannian that is sufficiently large, and what that means is I want my Grassmannian to be of dk spaces in capital N, and capital N is little n plus the difference of dk and d1. So think about it as all the number of indices you need to fill up a d1 minor to be a dk minor. And then I can define a map sending a Plucker coordinate capital Pi of the flag variety to a Plucker coordinate lowercase pi in the Grassmannian by just filling up. And the way I fill up here is just adding the indices n plus 1 up to n, whatever cardinality I need. And this map, we show that this map defines an embedding of the algebras, and it extends to an embedding of the cluster algebras. So it's exactly of this subcluster algebra type that we've seen on the slide before. So I wanted to do only 45 minutes of talk because of the excursion to have the coffee break earlier. So let me tell you a bit about the proof and then wrap up. So here's the idea of the proof, where we show the existence of a mutation sequence starting at the initial seed of the Grassmannian to a seed that contains all the images of my initial Plücke coordinates or initial cluster variables of the flag variety. And then we do this operation of freezing the right number of vertices to be in the case where we satisfy the definition to be able to take a subpattern. And yes. And okay, I copied this lemma to tell you a bit about the mutation sequence. So at least in the case of if my flag variety has 2 steps, we did this counting of how many mutations we need from the initial seed to get to the seed in the Grassmannian. And here's the big example. So maybe let's first check this one. This is the initial, so this is a big example now to illustrate well. This is the initial seed of the cluster of the flag variety 4, 6, 9, and 12. Whenever you see like just one column that corresponds to a Plücke coordinate being the corresponding cluster variable, when you see 2 columns, that's a quadric enclosure. So we have lots of 1 columns down here, and luckily these are Plücke coordinates that already appear in the initial seed of the corresponding Grassmannian. And then everything that is marked in red are quadrics, so they're not in my initial seed for the Grassmannian because it only contains Plückers. So this is something that I would have to get from the mutation sequence. And if I go to the corresponding quiver for the Grassmannian, so my Grassmannian here is 9, 12. 12 is 17 is 12 plus 5, so difference of 9 and 4. This is the initial seed of the Grassmannian. And then we identify this rectangular subquivers where we perform mutations. And in this case, we have 2 of these rectangles, one just being the first row and the other one being down here. So in these areas, we perform mutations. All the other cluster variables will either be deleted from the quiver when we pass to the subpattern, or they are already images of cluster variables in the flag. And after we perform the mutation, we end up with a quiver like this. And here we already did some freezing to separate the vertices. Actually, we've frozen everything that we don't need in the subpattern to get the cluster algebra for the flag. So this is just to give you an idea. I'm also happy to talk about the details of the mutation sequence, but I thought this was enough to illustrate. Okay.
And what's the analog of the numbers in lemma 4.2 for general partial flag variety?
Oh, we didn't do the general counting. But you can deduce it. You can actually take it from here because the mutation, so the general case is just repetition of the 2-step case. So you have to just sum up these numbers for every rectangle. Like for every 2 consecutive indices, you compute this number and then you add all of them up. Yeah. The mutation sequence of fixing one part of the quiver and another don't interact. Okay, good. So then let me end with some comments of what is related, work to this.
Sorry, can I just ask what your result, like, is there like consequences or like what does this tell you?
What does it tell me? So for me it was, first of all, a very curious observation because I always thought about flags being like the bigger spaces than Grassmannians. There's no... Is there consequences of exactly this embedding? I think it's more work in progress of what might be the consequences. There's nothing I can report on.
Okay.
Okay. Yeah, so one person that is working on consequences is Jonathan. I don't know exactly the state of this project, but that is analyzing how this restricted seed that I found in the Grassmannian, how that interacts with the positroid decomposition of the Grassmannian itself. Another student of mine is working on a similar result for changing the embedding. So we made a choice of how to embed the Plücke, how to extend the Plückers of the flag to Plückers of the Grassmannian. So we could make different choices, and a student of mine is working on a different embedding and finds similar results.
Sorry, could you, like, how is that not just like changing the order of the last decay, like, coordinates on
Yes.
your Euclidean space?
This embedding?
Yeah.
Yes, but the cluster structure is very much sensitive to this kind of change.
Oh, okay.
Yeah. Like in this case, you need to find another seed that has other kinds of Flickr coordinates or other kinds of cluster layers in the Grassmannian to make it fit. But it's so. I mean, so now for now we're analyzing two different embeddings. Both of them seem to work. This one is more complicated than the other in terms of writing down a mutation sequence. But it seems, well, maybe it's too early to say anything. But yeah, it seems like you can choose different embeddings. For now, that's all. There's more than one. Okay, and then let me end with some physics comments that are really super short. But I'm in the very lucky position of having Anastasia and Irma talking next about how these cluster structures on partial flag varieties are used and applied to the computation of symbols for sketching amplitudes when we have non-planar duality, non-Dewey conformal cases. And then there's this comment on the BCFW tiles. I think Matteo's not here, but yeah. So in the Grassmannian case, that's like the momentum twister case without the infinity twister. There's this very nice result by Lauren and Ron Tesla and Melissa and Chime and Zvika and Matteo. That the cluster structure, like the compatible cluster variables in the Grassmannian for n, tells you about tiles in the amicus-4 amplituhedron. And Matteo is convinced that a similar statement holds for the momentum amplituhedron using the cluster structure on the flag varieties 2 and minus 2n, which would correspond to spheres. Okay, that's it.
So in the momentum twister embedding of the kinematics, you say the 2 points are as special as the infinity twister, but you didn't have to take them as consecutive labels in the planar ordering. So can you find actually flags that are, that treat 5 and 8 special, non-consecutive pairs?
Yes, I was thinking about this just this week. No, I haven't. I haven't. I mean, I feel like to some extent it would just be applying a symmetric group action, and that's like an easy solution. Take this cluster algebra, but yeah.
Well, it's not the symmetry of the Grassmannian, though, right?
Yeah. Yeah. No, you can also. I mean, you can also apply the same permutation on the Grassmannian and get a different copy, where now you have other frozen variables. Just do it everywhere. But I don't know if that's a satisfying answer.
In these physics applications, so n is the number of particles?
Yes.
And is there an ordering on the particles?
I think for spin-elasticity we don't need it.
Oh, okay. Okay. So is there any meaning to positivity, which does depend on the ordering?
Yeah. Okay. Maybe I should not say too much because we have these two talks coming up.
Okay.
But I can say that we will need to consider more than one cluster structure exactly by changing acting with a symmetric group element on the Flickr coordinates, and then taking several copies of the cluster algebra where we change the frozen and so on.
Okay.
Yeah. So it's not just one cluster algebra that will tell you about positivity. You need several copies.
Okay. Thanks.
Any more questions? If not, then I think that we can let's thank Lara as well.